first approach is we're gonna take the optimal approach. To help us in the optimal approach, we're going to assume only 2 users. We're going to assume synchronization. And then we're going to talk about how to calculate the probability of error. We're also going to see, when we get to the end, that this approach is impractical for more than 2 users. Actually, it's practical for a few users, but once you get up into the, it's basically impossible to write down for 3 users. You could probably get a computer to solve it for up to a couple dozen users, but beyond that, it's intractable. Then we're going to talk about what's called the suboptimal. Excuse me, it's not called suboptimal, it is suboptimal. What we do in the suboptimal case is we ignore all the users except the user of interest. So we're going to pretend that the only user that's communicating is the one that we want to listen to. And there's interference from all the other users, but we're going to pretend that that's equal to noise. So this is much, much easier, and this is what's done in practice. But it's suboptimal. If you were able to take into account the interference, you could do better.
And that one's not synchronized, right?
Yeah. So this one, I mean, you can. These 2 assumptions we're going to use. They're just to make the problem easier. But you can construct the optimal detector when it's unsynchronized, when there's more than 2 users. We're just sort of going to see how. Basically, it's we're constructing the receiver the way we always have. So we're going to see how that works, because the approach that we've taken so far is optimal. Okay, so let's say we have 2 users. We're doing this first. So we have 2 users. And we're going to give them chip sequences. So I'm going to call my chip sequence vector H. I can't remember if I gave it a different notation last time, but I prefer to call it H. And I'll use the superscript brackets to indicate which user I'm talking about. So H1 is, let's give them chip sequence 1, 1, 1, 0, 1, 0, 0. So I think this is a shifted version of the maximum like shift register that we talked about last time. So in other words, if you give it a different initialization, this is that sequence. H2, unfortunately, there's only, like I said, there's only one such sequence. There's only one such, I think there's only one maximum like shift register sequence with 3 shift registers. So what I'm going to do to get the second user's chip sequence is I'm going to take this and time reverse it. Okay, my chips. What am I going to use for chips? I'm going to use C0K equal to +1 for 0 less than K less than, or excuse me, 1 less than K less than NC and 0 otherwise. And I'm going to use C1 of K is equal to minus C0 of K. So that is basically the chips are just polar NRZ bits. Okay, remember we're gonna be we're going to be using two different vectors to modulate the two different bits. So what we're going to do is we're going to construct this as a signal space. So remember, this is a discrete time function over here, but what we can do is we can call it a vector. So we're going to call C0 as the all-one vector of length nc. In other words, that's just the vector representing this, and we talked about that when we were doing signal space. And similarly, the C1 vector is equal to minus C0. So if we do that, we can assemble signals for we can assemble the modulation signals for both users. So firstly, we're going to assign each user a basis vector. So the user 1 basis vector is just going to be, we'll take this chip sequence and we will replace each bit with the corresponding chip. So S1 will be C1, 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 C0, C1, C0, C0. And by putting them all together in this vector like this, I'm basically saying, okay, this is a vector, and just stick that vector in. So these vectors are basically concatenated one after another. And it's also good to point out that this would be, I can express everything in terms of C0. This is minus C0, minus C0, minus C0, C0 plus C0, plus, minus C0, plus C0, plus C0. And my second basis vector corresponding to the second user's transmission is this. C0, C0, C1, C0, C1, C1, C1. And again, you can express that all in terms of C0, plus C0, plus C0, minus C0, plus C0, minus C0, minus C0, minus C0. Okay, so now what? Basically, if we want to send, we're going to use coordinates. The signal we're going to send is this. Let's call it X. And this will be some component in the user 1 direction. So let's call it alpha. Actually, let's call it B1. S1. And then some signal in the user 2 direction. B2. S2.